students to work on physics, biology, and chemistry throughout, so that they have like a good basis going into high school, middle school, and advanced courses if they choose to do so. But also we want it to be as engaging as possible. After all, it's a summer camp. We want them to have a lot of fun. So we want to make sure that regardless of the skill level of the students, regardless of the understanding of the students, that we make sure that those who are excelling are always challenged, and that those who are struggling, we provide them with support. So I'm with another partner, he's not here today, but we're gonna make sure that those who are struggling get the help that they need so that we can maintain the pace of the each day. And that way we have some backup course material if something is taking too little time and they're going through things quicker than we expected. And we also have course material we can move from one day to another day if something isn't taking the amount of time that we expected it to. And then we'll also end every single day with a Kahoot, just to keep things very light, keep things engaged. So the first schedule right here, this is the draft that we came up with, which is that the first week will be physics, because it's very simple ideas. At least we're going to simplify complex ideas, and I think it's a great science to introduce them to. It's a little more fun compared to the other sciences, because we'll do things like the egg drop, which is the one that I'm going to be explaining today. But we'll also have on day 5, structural engineering is just going to be a bunch of fun things to make, like Thermal machines is going to have catapults, but structural engineering, we're going to have like bridge building competitions. They're going to learn about bridge building and those kind of things. So it's going to be really fun. And we have experiments on almost every single day in most of these, just to keep all the students very engaged. So the egg drop, just some example materials that we have here. But regarding the egg drop, the best thing about it is that we can kind of just use whatever we have on hand, cardboard, whatever we end up buying if we have excess of it from other classes, for other science experiments. This is what we can use for the egg drop, because we need some materials that kind of, we know they're not going to work, but we want the students to think about why it's not going to work, right? Something very rigid is going to hurt the egg. It's going to make something very dense is going to increase the weight and make the egg fall faster. It's what they don't want. But they need to think about why they don't want that, right? So a lot of these materials that I mentioned here are good for an egg drop, but we might also have some things just to trick them a little bit. And these are the key physics ideas that I want to cover. We would also cover some other ideas as well if they're not struggling with these, but we need a little bit of struggle, but not too much. We want them to understand everything by the end of it, and I think within the time given, this is very feasible for them to understand. Just very simple understandings of all these ideas. There's no or little calculation involved, because obviously it might get too complicated for them and might get very hard for them to understand. So when it comes to these ideas, we're just trying to keep them understanding the topic, how it occurs in the real world, and how it occurs in physics, so that they have like that basis, that intuition developed about physics. So what is physics? So this is going into what this first day would be about. This is the egg drop day. So first week 1, day 1, physics. So first I'm gonna ask, what is physics? And whatever response that they give me here kind of helps me, especially on this first day, right? It helps me gauge what kind of crowd I'm working with, what kind of skill level I'm getting from these students. So there's just a definition of physics here, but my favorite definition is just physics of an approximation of nature, right? A lot of the stuff that we see in physics is just how something moves. If I kick that chair, how is it going to travel? How is friction going to affect the wheels of the chair, right? These kind of things. So I really want them to think about physics, how it's happening in the real world. And in all my demonstrations, I will try to use just real world examples to really make it easy for them to understand. And of course, I want to know what they already know about physics. If they know something about it, this makes it great. A lot of people have already heard about things like Newton's apple falling on his head. And these kind of ideas are great segues into actual physical understanding. So kinematics might be too complicated for them to understand, but to make kinematics simple, we do just talk about these main ideas of distance, displacement, speed, velocity, and acceleration. So to demonstrate distance, I can just walk across here and I traveled 5 steps, and steps are a unit. You can use any unit. You can use feet, you can use meters, miles, kilometers, whatever you want. But I've traveled 5 steps there. Now, if I were to walk like this, I've now traveled 8 steps, but I've traveled the same displacement. So displacement is that distance that I travel in a singular direction, while distance is how many steps I've traveled to get to that point, right? So that's the difference between displacement and distance. It's just very simplified, very quick. Of course, I'll spend a lot more time on that just to make sure that they actually understand it. Now, that goes into this idea of vectors, right? Because this way that I walked in a straight line can get represented by an arrow. I can draw an arrow to represent how I moved, and I can also draw multiple arrows to show that I turned here, I turned here, I turned here, and so on, right? So that's called a vector, and a vector represents something called a magnitude, which is the amount of something, and it also represents the direction. So for example, if I were to walk towards Oscar, my direction would be like this. If I were to walk towards the wall, my direction would be this, and the vector's tail would start from me, because that's where the direction is moving from. And a magnitude is the amount of something. So my vector to Oscar, if it was a movement vector, right, would just be from me all the way to Oscar. Now, what would happen if you had 2 vectors though, right? So think about this literally. If I went to Oscar and then I went back to where I was, that would be one vector and then another vector. So this comes to this idea of resultant vectors. So we have this vector B and we have this vector A, and when 2 vectors are added together, they create a resultant vector, which is this idea of the sum of 2 vectors makes a new vector that kind of, if moved from this position to the original position, is kind of the idea of what these 2 vectors do to the original object. And I can just make them understand that by making them move around, making them just try different things, right? Just stepping in a single direction works really well to make them understand resultant vectors. And I will also have some kind of worksheet prepared in case it is difficult for them to understand, because practice makes perfect to some extent here. So now, on the before I were to give them a worksheet, I would make them try themselves right here on the board. So, if a paper plane travels 4 meters forward and 3 meters up, what vector could represent this? So, a vector that could represent this, I will let them try, but here I'm not going to let you guys try. Would be, first, we need the 4 meters forward, and we need the 2 meters up, so 3 meters up, and that gives us this vector right here. This green resultant vector is the traveling of the paper plane. But a question that arises here is, why didn't I make the vector towards the negative numbers? And the reason why is because when we designate the use of numbers in physics, we're thinking about, hey, how do we demonstrate something that's happening in the real world, natural phenomena, to numbers, to physics, and to these ideas? And the way to adjust a number for forward would be a positive number, and backwards would be a negative number. So if this paper plane was moving backwards, we might use a negative vector like this. And it's still positive because we can't go through the ground, right? We would assume that the ground is the value of 0 for up and down. And finally, how can we find the speed of the paper plane? So, depending on how much math the students know, if they know the Pythagorean theorem, right, this makes things very easy because this is actually just a 3, 4, 5 triangle. So that would be of 5 meters per second. But if they don't know that, it won't take that long to teach them. But we have an accommodation of time for that if necessary. And I'm assuming that depending on the amount of students we have, we're guaranteed to have some people who don't understand the Pythagorean theorem. So it's completely fine. That can be explained within this time. So if you've ever seen this before, what does it remind you of? Well, hopefully at least one person knows about Newton and the apple. If no one does, it's fine, because this is still an apple falling. And whenever you see these lines anywhere in any kind of graphic novel, anything you've ever seen, what does it make you think of? Well, it makes you think of motion, right? So we get a vector to represent it. And one important thing that we're going to notice here is that the vector has to be in the center of the object and the vector has to be on the object. So unlike these lines behind the apple, we do need the vector to actually be on the object and denote the direction and motion of the object from the object itself. Now this vector would be representing velocity. Velocity is that idea of speed in a specific given direction, and the size of the vector is the magnitude of that velocity, right? It's the amount of velocity we have in that direction that we talked about when I explained them, like just a simplified version of kinematics, right? So that part would have taken a lot longer than I took to explain to you guys, just because it is a lot of ideas. And I would have covered acceleration very gently because it is somewhat complicated. I'm gonna go into acceleration now though. So gravity is a force, and forces can also be represented with vectors. And forces are not considered in kinematics because they add that acceleration component that we kind of glazed over here. And acceleration is how your velocity changes over time. So we have a constant velocity. I'm moving in this direction at a constant speed, direction and speed, right? But if I am accelerating, now I'm not moving at a constant speed or direction. There's different acceleration. And acceleration isn't necessarily always positive. For example, I just moved back right there. That would be a negative acceleration, right? So gravity is a force because it changes that velocity. It changes that direction of movement. It changes how the object moves aside from just the object moving in a certain direction, the object being not implicated by any forces. So gravity causes a force about 10 newtons, and you don't have to worry about this value. You can think about fig newtons and newtons, whatever you want to think about when you think about the word newtons. It doesn't matter too much, just know that it's a value for now. But this actually correlates to 10 meters per second for acceleration. So that is this idea that gravity is going to change the object's motion by 10 meters per second, right? That's our velocity of the object. It's going to move down at 10 meters per second, and that's going to increase by 10 meters per second. So here, just to make sure that they understand that idea, I would have a vector diagram on paper for them to draw a vector, and then between 3 different steps. So 1 second, 0 seconds, 1 second, and 2 seconds of that 10 meters per second or 9.8 meters per second vector being added per second, so that they really understand that idea of a force changing the velocity of an object or the speed of an object. And before that, they would have to tell me what direction they think gravity is applied in, but I think all of them would get that right. Now, I job, yay! So I would allocate about 45 minutes to an hour for this portion because it is somewhat time consuming. Depending on the amount of students I have, at max we'll do groups of 3, but obviously I'm not entirely sure what kind of demographic we're working with, but you know, it's whatever. And yes, we will use the egg cartons as one of the materials for the egg drop for sure, because it's actually very effective. So that's pretty much it. And then after we're done with the egg drop, this one question right here, which is that I just want to know what they think stopped the egg from breaking. And throughout this lesson, I don't cover things like pressure and like how a pinpoint of pressure on the egg versus spreading the force applied to the egg, because I feel like that might get too complicated and too much for them to wrap their head around if they're struggling with like the kinematics and stuff. However, depending on how much time everything is taking, how engaged they are with the egg drop, if they want to spend more time on the egg drop, we can spend more time on the egg drop. If they don't, we don't. And then we will use the leftover time after talking about kinetic energy, potential energy, etc., to talk about those ideas of pressure and other things that are applied on the egg. So, kinetic energy and potential energy, we're going to go into this. So when you were dropping the egg, at the top of whatever we drop the egg from, I'm not sure where we will actually, but we'll figure that out. The egg has no kinetic energy. And kinetic energy is this energy that happens during motion. So the energy of my foot as I kick in the air, I have potential energy in my foot because I have energy in my body, right? I ate food to get that energy. And now I'm releasing it as kinetic energy by kicking my foot. So it's the same idea here. When this egg, we're just gonna assume that this is an egg. When your egg is at the top, the egg has gravitational potential energy. It's called gravitational potential energy because that potential energy comes from gravity, which we learned about before the egg drop. Can you remind me what gravity is? Cool. I like how Oscar is just nodding his head. Alright, so the potential energy is the energy that the egg has before it hits the ground. So however high the egg is that gonna, how is that gonna change your potential energy? Well, if my egg is all the way up here, my egg has a further distance to hit the ground. If it has a further distance to hit the ground, what happens? What's that relationship with gravity that we saw in the vectors? Well, for every second that we let that egg fly, it's going to increase in velocity because gravity is adding 10 meters per second, right? So as we increase the height, we're adding more energy to the egg. We're adding more potential energy to the egg because that energy, when released, is going to get converted into more kinetic energy. So with that idea, when the egg is at the bottom, right before it hits the ground, which energy is higher, kinetic energy or potential energy? So, wow, really? That's crazy, Oscar. Okay, so hopefully they answer kinetic energy. Obviously, I'm going through everything a lot faster than I would with them, just to get the idea across. But hopefully they understand that kinetic energy would be the highest at that point because all the potential energy from the gravity. Now, I'm not going to tell them, unless they're really, really understanding everything, I won't go into MGH, but the idea of H is important, right? How the height affects gravitational potential energy is something they should understand. For example, if I were to drop the egg from a shorter height, why does the egg travel slower, right? As the egg's falling, regardless of whatever parachutes they make with the coffee filters, whatever, the egg starts to increase in speed. Why do they think that happens, right? And that is a segue into this next idea, terminal velocity, yay! So the object has terminal velocity when that air that we're surrounded by and the force due to gravity comes to a balance. Because now we're back to kinematics. When these two force vectors cancel each other out, it's like me going in this direction and me going back. Now there's no displacement. Same idea here. These two force vectors cancel each other out. And now there's nothing happening to the ball except for the velocity it already has. And that's the idea of terminal velocity. So if we add a parachute to the egg, we increase what? Now hopefully they understand that the parachutes are affecting the air, right? And if they don't understand that, that's what I'm here to explain. But as they add more parachute material to their eggs, they increase that air resistance force. They increase the amount of it, they increase how fast it happens. And that way, this terminal velocity occurs earlier and it's a lot smaller than the terminal velocity if I just dropped a plain egg. And that's the goal behind this egg drop, right? We want to slow down the egg to a point where it's not going to break and hopefully it doesn't break. Also, just to avoid a mess, we are going to keep the eggs inside the Ziploc bags, you know, just for the sake of it. But yeah, that's pretty much the explanation for terminal velocity here. I don't know, but okay, yeah, there we go, that's there. But, so, behind that idea right here, what do you think his flight path will look like? So, this is just the velocity time graph. Now, I'm gonna go into these graphs in more detail, obviously, because I don't want them to be overwhelming. I think a lot of the ideas here might be very overwhelming for, you know, 4th and 5th graders, but that's why we're gonna go through everything really slowly, make sure that they understand an idea before moving on. And it's not gonna be quizzes or anything, because I don't want to put that kind of pressure on them necessarily, but I do want them to make sure that they can test their knowledge in some way, whether that be a Kahoot at the end whatever it is, but also testing their knowledge in between the lesson, just really making sure that they understand what something is before the next step. Because if I'm at this point in the lesson, this is towards the end of the lesson, and they don't understand what velocity is, this is gonna look very foreign to them, right? So they need that understanding of what velocity, or at least what speed is, because speed and velocity are very similar, right? Even if they forget about the direction part of velocity, they can still understand this to a good enough extent. So going into this idea of terminal velocity is that maximum velocity that we can achieve, right? So in that previous example, where the egg, or the tennis ball in this case, is being matched by the force exerted upwards by the air, and also the force exerted downwards by gravity, now the ball is no longer being accelerated, right? That idea of acceleration. And because of that, we only have velocity on the ball now, right? The velocity that gravity acted is still there. The velocity isn't being affected by anything. So that is our terminal velocity. It's going to stay constant. So that's shown here, where we can ignore this part right here. This is just something being launched to a terminal velocity. But you can also assume that this is where he opens his parachute, right? And as he starts falling, this is his velocity, right? His velocity vector going down. And we can see that this is really steep. This is really fast. But as he starts reaching the ground, he reaches a terminal velocity because of his parachute, because that force of the air, because of how big this parachute is, it can trap all that air, and the air will push up against him while gravity pushes down, and eventually he will reach a very, very, very slow velocity that'll let him reach the ground safely. And then we just have a Kahoot that I'll make a Kahoot that's like specific to everything we studied, just so that it's not like too hard to too different from what we studied, right? So I don't want it to have any like equations or anything. And then after that we'll have one fun Kahoot afterwards, just to keep everything pretty open. And that's it. Yeah.
I think we have QA part, yes?
Yeah, question.
Yeah.
So 5 minutes. So very great. So I have just something I write here. Do you need some paper materials for the kids?
I mean, I can just print them out. It's not gonna be.
Just print
Yeah.
them out. Okay.
It won't be that hard.
Okay. I think you students, I think perhaps you need make easier for the kids, because the kids I found they just fourth and fifth grader. So perhaps you need some add more games, more experiment, more videos, and less words. And you can ask some students involve you discussion. Yeah.
Okay. Yeah. So yeah. Okay. I mean, yeah. So wait, there is one thing I did forget to talk about, which that's a really great point.
Yeah.
Is that like basically during whenever we have like these questions, right? Like, for example, how can we find the speed of the paper plane? Like I do want them to, if there's enough of them at least, I do want them to talk with us, me and you, and also talk with themselves. We can put them in groups.
Yeah.
If there's enough of them, and if there's just a few of them, then they can all just work together. And we do want them to discuss these ideas and really think about it if they can. And yeah, I am worried about these ideas being too challenging for 4th to 5th graders, but that's also why, depending on how, what kind of reception I get from them, I will either, dumb it down to some extent, or I will go slower through ideas, and we can kind of just cut out portions of this that are too hard to understand. For example, we might just completely ignore those ideas at the end about terminal velocity and those kind of things. The real main goal here is for them to understand vectors and gravity, which I think are simple enough for them to understand. If kinematics is too hard for them to understand, we can also...
the kids prepare all the materials, or you can prepare for the kids?
We can prepare for the kids.
Yeah, that's okay. You can have $100 budget for your materials per week. Yeah.
Okay. Per week or?
Per week.
Okay. Yeah, that's perfect.
Yeah. Give me your receipt. You can add some outdoor activities. Yes, also.
Okay.
Yeah.
Yeah.
That's great.
Do you have any suggestions though?
I'm not sure. Just like I found you smooth different way like that. Yeah, perhaps the I'm not sure it's vector. Yeah, you can ask some kids working different way. Yeah, just introduce that things.
Yeah, I'm also thinking about like having them just with like a yardstick. Yeah, I don't know. I just went to the end of the slideshow.
Yeah.
Okay, so like with a yardstick, I can just have them measure out a distance that they travel. They can walk across and then walk in different, and they can like make vector maps or something of how they're moving. Just whatever they struggle on the most, we'll spend more time on. Which I'm assuming is going to be kinematics. I think that's going to be the hardest thing in this entire lesson. So we might end up spending, you know, we might end up spending all the way back here. It's in the beginning, yeah. We might end up spending 30 minutes on just this slide before we move on to vectors, and that's fine. That's perfectly fine because I do think that this is probably the most important thing about the entire lesson as well.
So I guess like, are you gonna have like homework or like practice problems to like make sure they have no homework? Oh, never mind.
I will have practice problems during class though. In this first class, I don't want them to have too many equations to work with, especially since we're gonna be diving into so many ideas. I'd rather make sure that they understand something. I don't want them to just, you know, crunch numbers or memorize displacement over time for velocity. I'd rather have them actually understand and then be able to explain to me what is the difference between distance and displacement. What's the difference between speed and velocity?
Okay.
Right? So.
That's the questions.
That will be breaks. So what are you doing breaks?
Yeah, we are doing breaks. I kind of didn't talk about that.
Shouldn't we like have all the classes time their breaks like at the same time so then the kids can play with other kids from different classes?
Yeah, that's a good idea.
Great idea.
That's a good idea, yeah. I mean, whatever you guys come up with then will work perfectly within this. Basically, similar to how the egg drop is just right here, like right here, right? This egg drop is, it's not like not a break, but it's also kind of a break. So like right here, because we'll take our time with this. But also, I think right before this slide, this would be a great time for like a short break for sure. So, but it does just, this is very flexible. So whatever you guys find to work as a great break timing for the other classes, we can just implement right into this. It'll work perfect.
So if you don't have to go through all the slides, right? Like,
no.
Like this is just like all the material you have just in case they get through all of that. But like,
no, actually I would have even more ready because it is a long time at the end of the day. So depending on how quickly they're getting through, right? I might talk about Newton's laws as well, including this, for example. I think it's a great idea to introduce them to Newton's laws because anyways I have to do that in day 2 for simple machines and stuff like that. So if they have that in their mind ahead of time, it does make day 2 progress a lot easier. So it completely depends on how their reception is of the ideas.
okay.
Thank you.
Alright, that's good.